Welcome all. So today we are going to see the continuity of the searching techniques, and that is uninformed search methods. So today we are going to see like the uniform cost search method and depth limited search method. So in the uniform cost search method already we have discussed like one problem and follow by the procedures also, and then we can continue with the other example today. So already just to recap for the uniform cast search method. So this is one of the traversal method, and we can just making with the property tree with the weighted value, and then we can find the lowest cost price. Okay, we can just find the optimal cost price here. So that is very important, and we can make with the priority queue also. Okay, so this is the thing. And uniform cost search method, this is one of the traversal with using the weighted tree with the following by the graph. Okay, so we can make with the tree or graph making level, and follow by the we have to reach out the final optimal solution with the cumulative cost. That is very important. And this is graph or tree, we can just always dependent to the optimal cost, that is a value. And this is we can just implement with the help of the priority queue. Okay, and this search method we can just using with the BFS method. Okay, so we can just take with the help of BFS method and maintaining the path cost, that is a breadth first search method. And this is as here one of the information search already we know. And it can be just expand the node with the lowest cumulative path cost, and then using the priority queue. And it always select the least cost path and before the exploring the all path and we have to just ensuring the optimal solutions when all the edge cost and they are positive. That is very important. And then we can just make with the breadth first search always we can use, but we have to just consider for the where it should be just we want in the step size. Okay, that also we have to observe. And this uniform cost search method we can just consider the path cost and instead of the search depth. Okay, that is very important. And it is widely used for the route planning, and then GPS navigation system, and then the robotics, network routing, and then other real-time applications. We can just find for the minimum cost of the path level. So this is the real-time example for the uniform cost search method. Okay, so this is the thing. And the main thing is what now we can just consider with the path cost and then the instead of the search depth. That is very important thing. We can take with the help of like the BFS method, we can approach this process level. Okay, and this is the sample diagram for the uniform cost search method. So we can just make with the level, whatever the level it should be just given in the graph and then tree. Okay, and we can make with the starting as the 0 and then 1 and then 2 and then 3 and then 4, we can just fix it. And follow by the uniform cost search, we are having the just node representation of name, and follow by the we are having the proper value for the each node. That is very important. And we can just support for the like a BFS method, and then we can support for the just we can take the support for the priority queue. We can find the lowest cost. So whenever we can just approach with the each level, we could just find the lowest cost with the comparing level. So when we can just compare to the parent and then child node, so how many nodes it should be just connected into that. Okay, so that also we have to observe with the help of the BFS method. That is very important, because the S is as the parent, and the S it could be just connected as the child node for the A and B. So A and B is there, but whenever we can travel from the S to A, again we have to check with the nearest node of B. So these the time we need the help of the BFS, that is a breadth first search method, because then only we can just move on to the nearest node, and then we can observe with the what is the value it should be present in the nearest thing. And we can just apply with the uniform cost search method as the lowest cost, and then we can just fix with that particular node and then travel with the other position. Okay, so that is the main rule for this uniform cost search method. So now we can look at this example. So S as the parent node, and we are having the AB method, AB as a node, and the A what is the value it should be present. They have given the value for 1, and B as the value for 4. Now we can just compare with the value with the help of the BFS and then the BFS and then the lowest cost rule. So the one is the one of the lowest price. So that's why we can just fix with the A as the position of the node. Okay. Next we can move with the level 2. So we are having the three kind of the levels. Okay. So but what the thing we can just use now, we can use with the BFS method, and we can just see with the what are all the values that can be present in the each node. So here the C it having the 3, and then D it having the 2, and then G it having the 5. Okay. But here we are having only the connected node itself like the D. So there is no other way. We can just move into the these position. Okay. And then next we can just go with the like the G as the final node. So they have given the problem for G as the final node. So directly we can just give with the value connection with the G. Okay, so these are all the path costs. So we are using the 3 plus 2 plus 1. Totally we are having the 6 as the optimal solution value for we can reach with the S to D. Okay, S to G. Okay, so this is one of the example of the unicast search method. So the next example for the uniform cast search method means, so this is one of the graph. So yes, we can start with the S, and then as a starting node S, it will be just replicate to the A and B, and then C, D, E, and then F, G, H, I. Okay, so the path cast S to A as the 2, and then S to B as the 5, and A to C as the cast is 3, and then A to D as the cast is 4, and B2 connected with the only one node as the E, we are having the 2, and simultaneously C2 F we are having the 6, and C2 G we are having the 5, and the D it will be connected to the H, and we are having the path cast is 1, and E it will be connected to the I, we are having the path cast is 3. Okay, so this is the starting node. Our goal node is what now? We have to reach out, our goal is H. Okay, so we have to check the these level. So now we can fix with the level. So S as the level 0, and then level 1 it should be considered as a and B node, and then level 2 we can consider as a C, D, E nodes, and then level 3 we can consider as a F, G, H, I. So these are all the node level of representation. Okay, so our goal node is H, so that the thing we have to reach out. Okay, so here we can just make with the what is the cost with the node of the value. Okay, so and then what are all the node it should be connected into that, just we can just maintaining with the some level. Okay, some datas. Okay, so yes, it will be connected to the A and then B the position, and what is the optimal value. And the same time the A it should be connected, it should be just connected with the C and D, and what are all the value it should be present. And the same time the B it should be connected into the E, and what is the value. And see what are all the nodes it should be connected, the F and then G it having the some value like the optimal value, and the D it will be just connected to the H and it having the particular value. At the same time E it should be connected to the I, it having the some particular value. So these way we can just record the information for the graph orientation thing. And next we can move on to the step 1. Okay, so S as the starting position. So that's why we can just make with the 0 as the starting position. Okay, now we can just take with the help of the priority queue. So now what the thing, S as the starting position, we can just connect with the what are all the connection it should be made. Okay, so A and B as the connection, and we are having the 2 and 5 as the value over here. Okay, so here we can apply for the BFS, because the S it will be just to take with the A means simultaneously we have to just to trace out the nearest node also. Okay, that's why we can just make with the BFS method. And here the 2 and 5 is there. Okay, like what now A and B is there, so we want to just take with the values of that thing. So 2 and 5, so 2 and 5 we have to check. Okay, so with the help of the like the lowest cost method, we can just find the which is the and what is the minimum value here. Okay, so now we can consider 2 and 5 as the optimal value for the connected thing. So now we can fix with the 2 as the minimum value. Okay, so that we can just expand the next position. So level 1 also we have fixed with the 2 as the minimum cost of the value. Okay, and now we can just move on to the step 3 process. So what all the thing we are having, so S as the first step, and then A we have note down the eighth position of the value. So now we can just make with the Q representation what all the connectivity it should be there. So A as the current position on the previous level 1. Now we can move on to the level 2. Okay, we are having the nodes for what are all the level nodes. So B of 5 in the previous, and C of the 5, C of 5, 3 in the previous the thing, and D of the position of 6. Okay, so it having the like what now, it having the expanding the form. Okay, so that the thing also we have to observe here. So A, and then A it should be connected to the like the C and then D. So here we want to just move on to the which is the lowest one. Okay, so that also we have to observe. And the next one we can expand into the other form is what now, we can just move on to the next portion, like the expand to the B. Okay, so now Q we have to just maintain the C of 5 and then D of 6 and then follow by the E of 7. Okay, so that also we have to maintain for the following, for the step for the connectivity of the previous node. And the next one, the expand the step of the 5. So expand the C, what are all the possible way we are having, like the D of the node position, and then E of the position, and followed by the G of the position, and then F of the position. Okay, so these are all the node of the representation here. Okay, so that also we have to just, this is also the moving steps, so we have to just record the q numbers. Okay, and next one as the step 6, so we have to just observe with the expanding of D. So what all the thing we have to move in the previous, we are having the node of E and follow by the H and follow by the G, and G it move to the F. Okay, so this is one of the overall the representation for the connectivity of the step size. And next one, okay, so next we can move into the goal node. Okay, so here what the thing is happening means, so here we are having the 8 is there, and then 8 sorry, S is there. So finally we have to reach out the H. So what are all the things we have to follow? Already we have recorded the information in the path cast of like what is the path cast, and then steps cast also happening over there, and it will be just useful and creating the making with the good level of the path cast. Okay, so now we can continue with the thing, like what now, the first we can observe with the S. Okay, S as the starting node. So what is the value we have already found? 2 as the minimum value, and follow by the A as the fixed position. Now we can just check with the what all the connection node it should be present in the C, in the 8th node. So we are having the C and D. Okay, so we have to check with the rule of the thing. Okay, and then D as the path cast of like the 4, but we have to just make with the thing for as the position of like what now, the 3 1D as the lowest position. But once we can just check with the 3 means we cannot just catch with the node of H. So that is the main drawback over here. So what the thing we should do, we should take with the like as the Dth position as the correct way for connectivity for the H. Okay, so that's why we can just pick with the D as the cast, as the maximum level of the cast. And next we can move into the H level. So because of the thing, the reason is what now, we are having, we cannot, once we can fix with the C means we cannot able to jump into the H position. Okay, that is the main drawback. So that's why we can just take with the node for the D and follow by the H. So that is the main drawback. Okay, so we cannot do anything, because once we can fix with the 3 follow by these node now, we cannot able to just find out these H position. That is the main drawback. That's why we can just fix with the, even though we are having the highest value for comparing the C node now, there is no problem, we can fix with the D as the position over here. Okay, now we can just check with that and then implement into the H position. Okay, so now what all the our path cast is like what, the 4 plus 2, 6, and then 1, 7. So total number of the path cost is 7 we have reached out. Okay, so this is the thing is happening for the uniform cost method. In previous, we can just maintaining the priority queue also. So what is the current position of the priority? It will be just connected into the each level of the presentation. Okay, so in the previous one, we can just move on to the like what now, like each and every node we have just maintaining the queued position of the node. So that's why we can just make with the each level of the queues representation. Okay, so that's why we can easy to solve out the each and every node of the level of making the proper tree. And this is one of the optimal path cost which we are going to compare into the queues. Okay, so what are the optimal path we are having, we can just find. So S followed by the A and followed by the D and then D followed by the H. Okay, this is the proper route for making our optimal path route. And then what is our cost as a minimal and then good optimal value for 7. Okay, so that is the thing here. One drawback is that the drawback is what, once we have fixed with the C now, we cannot able to reach out the H position. Maybe we can come with the these position all, we cannot just adding the optimal value only, we cannot able to reach out the H position. That is the main drawback of the thing. So that's why we can just pick the value for Dth position. Okay, with the minimum cost of the value. Okay, so this is one of the step process of the travel tree. Okay, it travels making the tree. As followed by the A and A followed by the B and then B followed by the C and then C followed by the D and then D followed by the H. So this is one of the proper thing, because we have to just maintaining the BFS method on always the making with the Q. Okay, so S followed by the A and then A B, we have to just compare into this, and at the same time once we can fix with the A and followed by the C and D. So what is the position of the value, it should be it should be present in this. So we have to just go with the fixed with the Dth position and then we can continue with the next row. Okay, so this is one of the proper tree path cost of the movements. Okay, so the next one is as a uniform cost search method. So here we can just analyze with the time and then space complexity over here. Okay, so the thing is what now, the first one always we can just analyze with the 4 component. So the first one is as the completeness and then time complexity and then space complexity and then optimality. So the first one, completeness, so we have to just complete the all steps of the process and we can successfully reach out the final goal also. Okay, with the minimum path cost of the level, that is very important. Okay, and the next one is as the time complexity. So time complexity, we have to just maintaining the cost of the optimal value depends to the thing, and the epsilon is the each step to get the closer to the goal state. So that is very important. And the number of the step size is C star divided by the epsilon plus P1. Okay, the step size plus P1. Okay, so we have taken the plus 1 as the additional as the formula here. So we can start with the 0 until the end of the process. Okay, so here this is one of the time complexity. The final the formula is like the big O of B of power 1 plus C of divided by the epsilon. Okay, that is the number of step size. So this is one of the taken for the step size of the thing. So we can just consider as the state of 0 now. Okay, so that is the thing, and this is one of the step size. Okay, but the thing is like what now, whenever we can move with the process, okay, it will be just handling the proper way. And B as the node of every state, we can just observe the level of the every state of the process. Okay, so this is one of the time complexity. So we have to maintain the time complexity with the help of the BFS, and we have to analyze with the what is the main role of the minimum value. Okay, so that also we have to analyze for the each thing. So that's why the time is, it will be taking the some time thing for analyzing the each level, because the time constraints is very important for the time complexity. And next one, space complexity. So space also it having the some complexity is there because of the worst case space, because what now, it having the some lot of taking the time for analyzing the low cost of the process, so that's why it will be taking the more spaces also. And because what now, every node we want to check, so then only we can decide with the which is the minimum value. So that's why the space is it will be needed for the more. Okay, so that the formula is what now, big O of B of 1 plus the C star in the divided by the epsilon. Okay, the B as the every state. Okay, and then follow by the 1, and the number of the step size is C star the C plus 1. Okay, the C means as the cost of the optimal solution. Okay, that is the important thing. And next one is as the optimal. So this is one of the optimal cost level. Definitely it will be the optimal cost level. Definitely we have to just always we can fix with the lowest price level only. So that's why we can call it as a optimal optimality and then optimal solution. Okay, so lowest thing only we are going to decide. Okay, so this is the sample and then another example of the uniform cost search method. So here the first example we have just made with the tree for the proper structure away. So like what is the level of node, it will be the present into the next level. So the connectivity process also very easy like the lowest node. But the second example we are having the some drawback for the C and Dth position because of the value is higher. But anyway we can just reach out the final goal. So that's why we can just move on and then fix with the Dth position, and then we can just roll into that. Okay, that is the thing. So this is called as a uniform cost search method. And next we can continue with the depth limited search method. Okay, so depth limited search method, this is similar to the depth first search method. This is one of the predetermined determined limit. Okay, the main drawback for that is one of the infinite path in the DFS method, that is a depth first search method. Okay, so this is one of the combination of DLS and then DFS method. Okay, this is not and the optimal solution of the value. Okay, that is important thing. And we can just see this is how it will be not considered as the optimal value, because this is one of the level based search method. And this algorithm, the node, it will be just analyzed with the depth limit, and it has there is a no successor node of the further. Okay, so this is one of the under that the like the uninformed search method only. Okay, so because this is the connectivity of the like the node, it having the predefined depth limit, and it will be just to prevent the search from the continue indefinitely in the deep or infide the search spaces by restricting the exploration beyond the specified limit. That is very important. And these depth limited search method uses the stack or recursive for traversal the each and every tree, and it can be just to require the less memory and then breadth first search method. And it commonly just used in the artificial intelligence of real-time applications, and then problem means for example game trees, and then problem solving situations, and then the maximum search depth is known in advance. So these are all the thing for the main advantages of the application. The main thing is what now, depth limited search we can just find with the limit of the tree. It should be present in the form. That is the main important thing. So this is the problem. So depth limited search, we are having the start node is S, and then the end node is J. So first we can just roll out the depth limited search method. Okay, so here we can just apply with the depth first search and as well as the BFS, that is a breadth first search also we can just apply into that. But breadth first search, it sometimes it will be taking the more memory, sorry, less memory. Okay, for traversal the value. Okay, traversal the process. Okay, because it will be just to combine the DFS and then BFS method. First we have to just analyze the depth level, and simultaneously what is the goal node is it should be present. Based upon the goal node we can reach out with the help of the BFS method, and then we can just travel into that. But whenever the DFS method is happening, definitely we can use with the recursive algorithm, that is a backtracking process, it will be applicable. Okay, so now we can discuss with the thing. So starting node is S and then ending node is J. So these are all the level based, level 0, level 1, level 2, level 3. These are all the level based of the allocating of the process. Okay, so first one we can start with the S position, that is a starting node. And the limit is they have given, and the position of the node also they have given j as the position. That limit is level 2. Now we can use with the depth process. Okay, what is the depth process here? So s to a and a to c, this is one of the depth process here. Okay, so now we can just apply for the what is the technique we need to apply, because dfs already we have used. And what is the technique we have used here? Like the recursive algorithm of the backtracking. Okay, now we can use with the backtracking of d, and now we can just switch on to the backtracking of the b, and here the bfs also it will be using. Okay, because the we can analyze the left to right position. Okay, so now we can use with the depth, that is a dfs method, b followed by the I. Okay, so b followed by the I, we can just move into this. Okay, and follow by the backtracking method we can use with the j. Okay, so here we can just use with the bfs for the a to b with the help, and whenever we can use with the backtracking, so we can use with the like what na depth limited search. So the level size is 2, and then we can reach out the moving is what na j. So here we have applied the two technique for handling this process. Okay, so this is the first example, and follow by the process is what na, it will be just to indicate the problem does not have the any solution, but we have to just find out the limit. Okay, that is important, and the depth also. Okay, for this problem the advantage is what na, the depth limited search is the memory efficient, because we can just unwanted thing we cannot able to use that. So we can use the proper memory process, and then we can use the proper thing. Okay, for analyzing the each level of the representation, because the starting node and level everything they have given, we can analyze the using the based upon the level, and then we can just move on to the with the help of the bfs and then dfs method. And the main disadvantage is what now, this is one of the incompleteness process. Yes, why? Because we cannot able to see the all nodes in the particular graph and then tree, because of the limit they have given. Okay, certain limit they have given. In the previous example also they have given the level 2, so we cannot able to visit the level 3 or 3th of the node also. So we can just wind up the like until the starting to level 2 only. So we cannot able to see the what is the node it should be present in the level 3. That is the main disadvantage. Okay, the next one may not be optimal if the problem has more than the one solution. Okay, so we cannot able to see the all nodes. That's why we cannot able to consider this is not, this is as a like the proper optimal solution. Okay, because we cannot just see with the all node. Okay, we cannot able to find with the all node, so that's why we cannot just tell ensure with the this is the correct optimal solution, we cannot able to tell. Okay, so we can just tell the this is as the not optimal solution only, but we can just find out the limit, and then final goal solution also definitely we can find it. Okay, so this is one of the process flow. Whenever we can just go with the a b c. Okay, and then first we can fix with the a b d, and c also we can focus, and follow by the backtracking to the c with the help of bfs, and bfs it will be just connected to the next node. Okay, this is the working principle. So this is one of the other example. So depth limited search, we are having the verification of dfs method, where the maximum search depth is specified. This example has the two things. Okay, starting from the node of s, and then the algorithm explore the left subtree until it reaches the node of c at the depth 2, and the depth limit has been reached with the thing, and cannot explore the g and h because of the limit constraint. So they have given the limit constraint, so we cannot see with the upcoming the nodes also. And this algorithm the backtracks also using, and then explore the node until the what is the node it should be present in the goal state. Okay, and it having the right subtree and then connected with the b, and also the I as the goal node here, and the depth 3 process also it will be just to reach out, and the final goal we have to find out, but we cannot able to find for the goal node. Okay, that the reason we can see. Okay, for this problem. So the first one, DFS, depth limited search, they have given the tree structure for, this is the tree structure. Okay, so first we can fix with the level. So S as the level 0, and AB as the level 1, and C, D, E, F as the level 2, okay, and then GHI as the level 3, and then J as the level 4, okay, 0, 1, 2, 3, 4, okay, this is the level based. So what are all the level we are having? 4 level we are having, 0 up to the 4 level. But the depth limit they have given like the 2. 2 means where we can just wind up level 0, level 1, level 2. We have to wind up the level 2. But the goal node is what? Actually goal node is I. So we cannot see with the goal node also for this problem, because the depth limit they have just sort out, they have given like what now, before seeing to the like goal node. Okay, so we cannot able to see the goal node, because the reason is what now, they have given the limit of the search here. Okay, the 2 as the limit. So after the limit we cannot move into the next portion. So that is the main drawback. Okay, we can see the example now. So first one, step 1. Okay, so first we can start with the root node here. Okay, so the current node is S, and then the depth is 0. Okay, so because now only we are going to go with the next portion. And the step 2, so here the S as the path cast here, S to A as the path cast. Okay, the depth is now we have to we are in the depth 1 limit. Okay, so visited the 8th portion. Okay, so now we are in the depth equal to 1, the limit is 1. Okay, so we can apply with the, what is the rule now? So DFS method, that is a depth first search method. Okay, we are analyzing the bth node also, because with the help of BFS. Okay, so now we can just move on to the step 3. So look at here. So S, A, and then follow by the C. Okay, so we have the path route is SAC, we have routed, and the depth limit is 2. So they have given our depth limit is what? 2 as a maximum limit. Okay, so depth limit it has reached here. Okay, so we cannot able to visit for GHI. Okay, so now we can just backtracking apply method, we are going to apply here with the help of the DFS method. Okay, so we can apply for the backtracking. We can just come to the position of D. Okay, so now we can just go with the step 4. What are all the path cast it should be present? Yes, A, and then D. Okay, D, now we are present in the Dth position. Am I correct? With the help of the backtracking. And the depth limit is what? 2. Okay, we are in the position of 2. Because the depth limit is reached, and we have to just move on to the backtrack. So backtrack, we can just move on to the D. Okay, so now yeah, so now we can just, because we have to visit the all city, but the system does not know like the next portion, because we want to just the limit of 2 level. Okay, the limit is 2, so we want to visit the until what are all the nodes it should be present in the node. Okay, so we have to visit for all node, and with the help of the D, okay, we have to just move on to the B node with the help of backtracking at present in the Bth portion. Okay, so the path is what? S followed by the B. Now we can just apply with the BFS. So BFS has the thing like the breadth first process. Okay, now we are in the breadth first. Now the depth size is now 1. Okay, the next is the B. We can just move on to the Eth position. Okay, and E. So what are all the possible way we are having the A, B, and then E as the root. But the position is the depth limit is what? 2. So the depth limit is reached. We cannot visit the I, because the I connection is D only, but we cannot able to visit, and the backtracking also we cannot able to do. Okay, we can use the backtracking. Sorry, we can use the backtracking, but the limit, the next level is we cannot able to visit. Okay, that is important. And now we can use with the backtracking process with the help of the DFS method, and then we should just go with the Bth position again, and then we just move on to the Fth position here. Okay, so we have moved here. Okay, so the next one, the SBF, we are in the position of depth limit is 2, and the depth limit also reached. Okay, we don't have any node, it should be present in the after the F, and then we have reached the depth limit also. Okay, and we have visited until the F. So S to F we have visited for the all node, that is the constraint. So what are all the node we have visited? S, A, C, D, B, E, F. We have visited the all nodes with the help of the depth limited search, but we cannot able to find the I goal node, because of the reason is what, we are having the limit of depth limited as the 2. Okay, so that's why we cannot able to find with the ith node, that is a goal node. Okay, that is the main reason. So now what are all the nodes? What are all the nodes we have visited? A, S, A, C, D, B, E, F. Okay, so now we want to just make with the tree. Okay, here graph here, but we cannot able to visit the ith node. Okay, so that's why we have mentioned here goal node I is not found, because it is the beyond the limit, the depth limit. Okay, beyond the limit. So that is the reason. So now we want to make with the tree structure. S followed by the A followed by the C, and then C followed by the D, and then D followed by the B followed by the E, and then E followed by the F. Okay, so this is one of the tree structure over here. Okay, this is the final outcome. So that's why we cannot just conclude with the not optimal solution. Okay, so because the goal node we cannot able to reach out, only we have satisfied the limit only. Okay, that is the thing. Next one as the thing, once maybe. Okay, this is the nodes not visited beyond the depth of limit. Once maybe that we can just move on to the beyond the limit, means what the thing is happening. Okay, so we can see that thing. So until F we have reached, am I correct? Until F we have reached, and not visited the city is G, H, I, J. This is the not visited the city. So we can make with the beyond the level of the depth limit. Okay, not visited the city, we can mentioning the GHIJ. The final result is what? Depth limit 2. Okay, and the goal node is I, but the status is goal node not found. Okay, the reason is what? The goal node is I, but the depth is 3. Okay, we are having the goal node is in the, it should be present in the depth, that is a level of third. Okay, level of third. So that's why we cannot able to find the ith node of that level. Okay, that the thing we have to just define into this. Okay, so maybe the beyond the level we want to just roll out this problem, means what the thing is happening. Yes, A, C, and follow by the G. Definitely we have to reach out, because the depth level they have given the 3, means we can very easy to reach out our final goal. Okay, so G we can reach out, and finally we can use with the backtracking process, and then H, and follow by the, again we have to go with the C, and then C with the using the backtracking, and then D we have to go, and D follow by the I we can able to reach out. Okay, so this is the process way. Once they have given the limit is 3, means definitely we have to do for this process. The limit constraints we cannot able to see with the like, and then we cannot able to find with the final goal. So that's why we can make with the not optimal solution over here. Okay, and so this is the thing. And final conclusion, depth limit is 2 and goal node is I. The status is goal not found. So that's why we can just make with the not optimal solution and located at that 3, and then search with the restricted to the depth 2. Okay, so now we can just move on to the time and then space complexity over here. So first one we can just discuss with the 4 component. Okay, the completeness, and then time complexity, and then space complexity, and then optimal. Okay, so here what the thing is happening, the completeness. So we are just visited the all tria, no. So that's why we can just make with the not satisfying here. Completeness is not working for this problem. First problem, what is the constraint they have given? So based upon the constraint we have visited, and second problem we cannot able to visit give with the completeness process. Okay, this is the does not visit the all cities because they have given the goal node, but we cannot able to, due to the limit of the depth, so we cannot able to see the all node. So that's why we can make with the this is not the completeness process. The next one is as the time complexity. Okay, so time complexity, always we can just talk about the big O of P of E. So here we are having the this E, E no sorry L. So L we can just take with the limit, and then B, and then oh, this is one of the each step size. Okay, so the L as the limit here. Okay, this is one of the time complexity. So definitely it will be just making with the time complexity, because it will be just taking the less time, because of the we can use with the limit. Okay, it will be observing the limit based upon the limit, and then we can use with the DFS and then BFS method, we can reach out the limit only. Okay, because it does not focus the goal, because what na the limit, what all the limit it is having, the based upon the limit it will be just visited the all nodes. So that's why it will be making the very convenient time for this problem. The next one as the space complexity. So space complexity also it's not taking the too much of the complexity for the space, because of it having the two technique, and it will be observing the limit, and then it will be processed into that, and then big O of B into L. So L for the limit here, and B for the like the breadth of step size. Okay, so that also it will be focusing. And the next one as the optimal solution. Definitely the optimal, the first problem is the we can reach out the optimal for the first problem. Second problem we cannot able to reach out, so that's why we can not given the not optimal solution for the thing. Once the constraint, the limit also we have to satisfy, and then we have to satisfy the final goal reach level also we have to satisfy. Okay, then only we can observe, we can just tell about that this is one of the good optimal solution. Otherwise we cannot able to conclude the good optimal solution. Okay, because the depth also it will be important, and the same time we need to just reach out the final goal also. That is very important. So that we can just observe depth limited search can be viewed the special case of DFS, and it is not the optimal even L greater than of D. L means what? As the limit, and greater than of the D. Okay, so this is the study as the step size of the method over here. Okay, so that's why D as the depth of the shallowest. Okay, so that is important thing. So we have to reach the limit and as well as the depth, so then only the condition it will be satisfied here. Okay, and we have to just analyze with the final path also, final cost of the like the final goal also. That is very important. Okay, and this is one of the comparison of the uniform cost method, and then depth limited search method. The first one, this is one of the searching strategy. So we have to just expand the node with the lowest cumulative path cost. So yes, so each and every level we have to just observe with the lowest path level of the cost here. Okay, at the same time, so we are having the depth limited search method. Okay, so we are having the depth limited search method. It will be explore the node. Okay, DFS, that is a depth first search method, and then as well as the breadth first search method. Okay, but it having the using the some certain, what is that, as a recursive method, and followed by the BFS also. Okay, this is one of the searching technique, but it will be observing the depth and as well as the like what now goal state. That is very important. That's why we can call it as a path, optimal path. And here we are analyzing the like what now the lowest cost only. In the previous unicast problem, previous already we have discussed the first problem. It has like we can easily reach out the minimum number of the uniform cost search, but the today's second problem we cannot just give with the good minimum level of the path cost, but anyway compare with the other node we can give the conclude with the other very less number of the path cost. But at the same time, whenever we can compare with the two node, the one is the high and another one is the less value, but the less value we can pick means definitely we cannot able to reach out the final goal state. Okay, that's why we can just consider as the little more of the compared to the less value, and then we can pick up that particular node, and then we can reach out to the final state. This is one of the other strategy for the complex problem. Okay, that is the important thing. The next one, it will be just the uniform caste search. Always it will be preferred with the priority queue here. Okay, we can make with the priority rule only. It will be make with the each and every level of the recording information, and then path level of the thing where it will be go, and then step size, everything it will be recorded with the help of the priority queue only. And then next one, it will be take like the stack method, depth limited search, last in first out, or recursive method. Okay, whenever we can use with the DFS, we can maintaining the recursive. Okay, so what is the last limit of the node, and then we can maintaining the last node, and then we can just travel into the recursive algorithm, and as well as the backtracking process we can just see with the other node representation. Okay, and the next one, node selection. So we are having the lowest path cost only, definitely, because the lowest path cost only, each node, each step it will be considered, then only we can reach out the like the comfortable node, and then go less value of the cost also. And then the depth limited search, it will be just focusing the deepest unvisited node within the limited search. Okay, it will be just analyzing the deepest node, but we can just maintaining the depth limit. So any time it will be just maybe the what is the depth limit they have given. At the same time, on this in this the level they have given the goal statement, there is no problem. The beyond the depth limit of the level, they have given the goal node, means we cannot able to visit our goal node. That is a drawback. Okay, and the next one, cost consideration. So consider the path cost. Definitely the uniform cost, it will be considered as the path cost. At the same time, DLS we don't have just my maintaining the path cost. Okay, so that is important thing. And the next one, depth limit. There is no depth limit in the uniform cost. Okay, so we can make with the only the level based, level 0, level 1, what are the level it should be present in the node. So that only we are just maintaining with the thing. There is no depth limit thing we cannot able to find here. And here we can definitely use for the predefined level of the depth limit. Okay, based upon the depth limit only we can you travel with the all kind of the nodes, it should be present in the graph. Okay, that is very important. But we can just reach out the depth limit, that is the first priority. Even though we can just reach out the our final goal, and then goal or that the thing not matter, but we have to reach out the depth limit. That is very very important for the depth limited search technique. Okay, the next one, the optimal feature. So here the yes as the optimal feature, because if the all edges cars are positive, and then we have visited the all node. Okay, but in the same time the DLS we can compare with the thing now, so we cannot tell that this is not as a optimal, because sometime whenever we can just tell with the like the constraints of the problem. So in the depth limit they have given, at the same time they have given the like what the goal state is in the at present of the same level, means there is no problem. At the same time we are having the depth limit is one, and then we are having the other level of the like the beyond the level of the depth limit of goal state, means we cannot do anything. Okay, we have to just wind up the and then see with the following the depth limit only. Okay, we cannot move to the beyond the level. Okay, in the depth limit. So that's why we can tell with the this is not as a optimal solution of the problem. Okay, the next one, complete. Yes, it will be complete and then visited the all node. At the same time, depends upon the depth only we can decide. Yes, if the goal is within the depth limit, means it will be just visited for the all node. Otherwise we cannot able to get the goal statements, we cannot conclude this is as the completeness process. Okay, that is the one thing. And next one as the memory usage here. Okay, so here we can just take with the high level of the memory, because we are comparing the all state. Okay, whenever we can go with the first some level based, we can just observe with the all level. Okay, like the nearest node of what is the nearest node and what is the value it should be present. Okay, everything we want to check. That's why it will be taking the more memory. Already we have discussed in the comparison of the four time complexity, and then complex completeness, everything we have compared. No, at the time also we have discussed the uniform cast search method, definitely it will be taking the memory usage is high. At the same time, the depth search method, it will be just low and then with the moderate. Okay, because of the reason is what moderate, because of the depth limit. Okay, so they have given the depth is very less means, so it will be just to wind up the process, and at the same time it having the higher than the depth limit means it will be taking the more memory. That is the normal thing only. Okay, and the next one, the best used for the finding the minimum cost path in the weighted graph. Okay, that is the thing as the very important, and then advantage here, the minimum cost with the weighted graph. At the same time here, the searching larger graphs when the maximum depth is known. Okay, that is one of the important. So searching, this is one of the large graph representation, because the maximum depth is there means definitely we have to search into the large number of the depth. But here we can just maintain the minimum cost. So that's why the weighted also very less only. Okay. And the main advantage here means what? The guarantee of the least cost method or as the solution. Definitely it having the guarantee, we can give the guarantee for taking the minimum level of the cost optimal solution. Okay, in the uniform cost search method. At the same time, here the prevent the infinite depth searches and reduce the memory usage. Definitely these reasons it will be applicable for the depth limited search method. We can just prevent the infinite depth search. Okay, unwanted search we can just omit that, and then reduce the memory usage also. Okay, so that also we can do it. So that's why we can make with the main advantages over here. And then main disadvantages for the uniform cost search means it will be require the more memory and processing time, definitely, because whenever we can compare with the nearest node and what is the value it should be present in the current position, we need the more and more memory also at the when we can compare with the node. Okay, so this is not a sufficient for taking the whatever the required memory. We need the more memory spaces, and the same time we need the more time also, because then only we can able to judge into the with the minimum and the least cost of the values. Okay, that also we have to observe. Okay, and at the same time in the DLS method, depth limited search method may fail to find the goal state, definitely, because in the depth position only and then limit the position only we cannot able to find our goal. Okay, and the beyond the depth limit, so maybe they have given the more number of depth means it should be present in the graph means definitely we want to go with the next process, so that why at the time it will be just a need for the memory. Okay, depends upon the limit of depth, so we can decide with the memory also. Okay, so this is the main difference between the uniform cost search method at the same time as the depth limited search method. Okay, so both are all the as the some advantages there, and then some disadvantages also there. Okay, so this is the thing. And uniform cost search method, already we have discussed one problem in the previous video. That is one of the easy to find the path cost, and then today's this presentation it having the some difficult complexity of the problem. Okay, so the reason is what? So we are having the two node, at the two node it having the some value. At the value whenever we can compare with the lowest value, so we cannot able to find, once we can pick with the lowest value means we cannot able to find the goal state. Okay, so that's why we have to just pick into the highest position of the value. So that's why we can just pick with the highest value when we can compare with the lowest one. Okay, so then only we can reach out the final goal. Okay, that is one of the complexity for the problem there. And then when compared to the DLS method, so the first problem it is very easiest problem. In the whenever they have given the limit, same limit only we are having the goal node. Okay, so that's why we can just easy to reach out our goal state, and then the depth also. At the same time, the second problem, it having some very complex. Okay, so what the complex is that, so they have given the limit, based upon the limit we cannot able to reach out our goal because of what is the reason. So the limit only as a very important for the depth limited search method. At the same time we are having the goal node is it should be present in the at the level of the depth, means we can easy to reach out our goal node. Otherwise we cannot able to reach out our goal node, the beyond the limit only there, means we cannot do anything. So we can just conclude the conclusion for that is the not optimal solution. So we have visited the limit and as well as the goal, means we can just define with the optimal path of the process. Otherwise we cannot able to define with the optimal process. Okay, that's the thing. But you in the uniform cost search always it will be just fine with the optimal cost of the value in the when we can compare with the thing. At the same time we are having the DLS. Once we can reach out the depth and as well as the goal node, we can just tell and then conclude with the this is one of the optimal solution. Otherwise we cannot able to tell with the optimal solution. Okay, that is the thing. And in the times and then complexity also, so you uniform cost search it having the like what now more memory and then processing time depends upon this reason. Okay, so that is the main drawback. At the same time the depth limited search, so here we want like what now in particularly the thing is we want just to observe with the beyond the limit, means it will be taking the more memory. At the same time we have only the very less limited and then less limited until that the we are having the goal state, means we don't get any bother about that. Okay, so we can use with the very comfortable memory and then time also we can easy with roll out our process. Okay, this is the thing. And the main uniform cost search method it will be taking the priority queue approach, and the DLS method it will be taking like the stack with the LIFO technique, and then recursive algorithm also it will be taking and then handling our processing flow also. Okay, that is very important. So this is the based upon the main strategy for the difference and then the definitions and then the thing. So these presentation we have just seen with the one simple problem and then one complex problem for the both cases. Okay, that is very important. Okay, maybe in the uniform cost search method we can just reach out our goal. At that time we have to just pick with the high level. Okay, high level of the path cost when we can compare with the lowest value. At the same time in the DLS method we cannot able to reach out the goal state, but we have to check for we have to follow for the limit of the value. Okay, so that the constraint we cannot get it our goal state. Okay, that the two complexity problem also we have just discussed for this presentation. Okay, so thank you.